All right, everybody, welcome to part two of our unit on rotational motion. And for this video, I really want to hit sort of the idea of net torque and some of the things we can do that sort of Newton's second law with torque instead of with just regular force, as well as conservation of angular momentum and rotational energy, rotational kinetic energy. These are the topics that are more likely to show up on the AP test. To be honest, that first video really sort of just sets the stage. Some of those, there's a chance that some of that stuff will show up more the ideas behind rotational velocity for angular velocity instead of linear velocity. If you recall from the AP free response questions we gave you, the questions with the ladybug and the disk, those first couple questions that deal with that really were from the last video, but this one is where we're more likely to see a lot of our free response questions asking about some of these ideas, as well as the multiple choice. Again, just like linear momentum, momentum regardless shows up a lot. So we want to start here with this idea of inertia, and we've talked about this this general inertia before. This idea that objects naturally have a resistance to change their linear velocity, and that is solely dependent, if we're talking about something moving in a line, regular force, that's only dependent on its mass. It doesn't matter how that mass is distributed, what that object's shape is. It doesn't matter. It just matters how much mass is there. So planets have some inertia, a baseball, whatever, a duck, I don't care. All it depends on is the mass. If you know the mass of that object, you can talk about its linear velocity. But with rotational, changes to rotational motion, we have what's called the moment of inertia, and that is the resistance of something to change its angular velocity, how fast it's spinning, or the ability to change how fast something is spinning. It does depend on the mass, but differing from regular inertia, it depends on what shape that object is. If something is a hollow sphere versus a cylinder versus a box versus any other shape you can think of, all of those are different. Even if they have the exact identical mass, they are either easier or harder to change their angular velocity. They have more or less resistance to that change. So here's just a couple examples. We represent that that idea of moment of inertia, sometimes called angular mass or angular inertia, or various other things, but we represent it with this letter I. So if you see the letter I, yes, we've used that for current before, but if you're talking about motion, it is your moment of inertia. I for inertia. Here's various different ways you can calculate that, but one of the nice things that Mr. Holloway and I have noticed, or really Mr. Holloway, is that the AP test doesn't ask you to calculate these values. A lot of times this I and a lot of these problems have been dealing with what's the word I want? These variables, or it just gives you straight up what that moment of inertia is. You don't have to memorize or realize really even how to calculate these. So we'll skip over that. And that brings us to Newton's second law of rotation. We've seen net force equals MMA for sort of Newton's general second law, and that acceleration is net force over mass. That's sort of the inertia version for linear momentum or linear movement. But we can also have net torque is equal to I alpha. We said alpha the other day was the angular acceleration, how fast something is speeding up, how fast it's spinning. And that is just net torque equals I alpha. So it's almost the exact same form, but we just substitute in this moment of inertia and the angular acceleration instead. Very, very similar, but not the same. And again, kind of like the last video, I'm not going to do many problems here. Again, I'm at home on my laptop instead of with the smartboard. Tomorrow, I will make a video that just goes through a number of actual problems and work through some of those and talk through some of those again. And here's a nice big problem that I'll probably look at tomorrow. This is some sort of very old note. Another problem, and this is where we're getting into net torque. So let me see if I can just read through this a little bit. We've got this board, has a mass of 20 kilograms, uses seesaw. That's really an old problem from the other day, so we'll skip that. This is all worked out. Or a practice quiz type of thing. Okay, so the biggest thing with and this is in our calculation, but I can talk about it a little differently. Let's see if I can go to another slide. Yeah, we'll go back here. The biggest thing here is that objects that have their mass farther out from the center or the axis of rotation, objects that have mass farther spread out. So if you think about an ice skater, I know we've talked about this in class a little bit, but I'll hit it again here. If you have an ice skater, that is a uniform mass. We're going to just talk about an ice skater sort of in two different positions. Let's say it's a 100-kilogram ice skater, which is pretty heavy for an ice skater. But anyways, if they have their arms spread out, sort of spread out all the way, it is harder for them to rotate than if they have their arms tucked together. If you've ever seen or watched ice skating or Olympic diving even, when those athletes tuck in, they can spin a lot faster with the same amount of force being applied because their mass is all smaller in. It's tighter towards the center. If you have all your mass close to the center, you have a lower I. So here, oh, I'm not really sure how this person is. Oh, so I think this is kind of setting up like a spinning disc, maybe a merry-go-round, and the person's in the center. If that extra mass from the person is really close to the center, we get this I value, and then there's ways to calculate it again, where the inertia, the moment of inertia, is 900 kilogram meters squared. But over here where that person's offset, they're actually farther out, so we've got more mass that is farther away from the center of that rotation. And because of that, the moment of inertia goes up. And there's ways to calculate that, but to the best of our ability to notice, it's not really necessary for the AP test, which is super nice. So because you are farther out, you have a higher moment of inertia. It's harder to get you to start spinning. It's harder to get you spinning faster. The more weight, or the more mass, I should say, that you have farther. So again, mass farther out is harder to spin. It has a higher moment of inertia. Mass closer to that center of rotation, that axis of rotation, that results in an easier object to cause rotation on. It's easier to spin it. And we've seen other things where something is on that sort of circle matters as well. Again, farther out from that last video, farther out means you've got a larger sort of linear speed. You're actually moving faster if you're farther out, whereas if you're closer in, you are not moving as far as fast. Now, the angle that you rotate through is the same no matter where you are on that object spinning. So if I'm very close in versus very far out and this object is spinning, we go through the same angular displacement, have the same angular speed, but linearly we have differing speeds. Faster if you're farther out, and you're sort of heavier, if you want to think of it that way, for angular movement if you have mass that is farther out. So one of the biggest ideas that has shown up on the test that we've seen is this idea of angular momentum, which is represented with the letter L. It is equal to I, that moment of inertia, times W, or omega, lowercase omega, your angular velocity. Just like we had P equals mv for linear momentum, P being momentum equals mass times linear velocity. Now we have angular momentum equals moment of inertia times angular velocity. And just like linear momentum, we have the law of conservation of angular momentum. If we don't have any torque from outside the system, then the angular momentum of the system at the beginning must be equal to the angular momentum at the end. Again, if we've got a system of objects where there's one or two or more objects, those individual pieces of the system can change their momentum without an outside force, but the angular momentum of that entire system cannot change. So again, the ladybug problem that we talk about in class will be represented here with this. Again, linear momentum and angular momentum, very similar equations. They look very close together, and you can actually get into actual linear speed from here because our uh, sort of this value we said in the last value that angular momentum uh, is identical to this v times r, that how far out it is, and that also sort of takes care of that moment of inertia, and you can actually do mass that way. Haven't seen that very often on the test, but just want to make you aware of it as well. So like I was saying earlier, with arms spread out for an ice skater, they have a very large, or not very, I shouldn't say very large, but a larger moment of inertia with a smaller speed. But when that ice skater brings their arms in, they actually start spinning faster. In this case, momentum is still conserved. Their angular momentum, whatever they've got over here, is conserved. But because this I got smaller, that means that the speed has to get larger. That angular velocity must increase to keep that momentum the exact same. There was no outside force. All they did was bring their arms in. That is a sort of an internal force that is acting. So because of that, the momentum must be conserved as one of the biggest things. If there's no outside force, there's no push or pull from outside of that system, then your momentum has to be conserved. So again, linear quantities, net force equals ma versus net torque equals I alpha, P equals mv versus L equals I omega. And now we've also got rotational kinetic energy. Again, haven't seen this a lot, but just want to make you aware of it. Kinetic energy, we said, is 1/2 mv squared. Kinetic energy of rotation is 1/2 I omega squared. So if something is rolling down a hill, let's say, or actually let's just make it rolling across a flat surface. Maybe you kick a soccer ball. It's got some linear kinetic energy, right? It's moving, it's got velocity, linear velocity, but because that ball is also rolling, it's got kinetic energy rotationally as well. And we'll see sort of some of the effects of that. It turns out that if you've got something that slides versus something that rolls, you've got different places where that kinetic energy actually lays. And if they have the exact same energy, total mechanical energy to start with, what will end up happening is the object that rolls will actually move slower. And I'll show you why that is on one of these other slides, I think, is some notes on that. So this is just a way to find it. It says find the angular momentum and the rotational kinetic energy of a hoop. And it tells you that the I value is mr squared. So you can calculate that. And that is all good and dandy, just some plugging in values. Again, I'm not super worried about that. There hasn't been much of that represented on the test, but see if I can do, here's what I'm looking for. So we've seen before, now let me clear up some of this if I can. There we go. Let's try to get some of this stuff out of the way. So I don't want to do that. And we'll do that. So when we talk about total mechanical energy, we tend to say that it is conserved. It's conserved quantity as long as there's no non-conservative or non-conservative force acting. So if it's just gravity, if we've got a hoop-shaped object in this case, or a ball or whatever, at the top of that hill, and when we talk about the total mechanical energy being equal, we have potential energy, which we've talked about before, kinetic energy, but because it's an object that rolls, it's one that rotates, we also have to include in this value for its kinetic rotational energy, or rotational kinetic energy, both at the top and the bottom. At the top, before we start, it's not moving sort of linearly. Doesn't have a speed sideways or up and down actual translationally, but it's also not rolling. So we can actually make both of those values just be zero, and we've just got mgh at the top. But as it goes to the bottom, no mgh this time, it not only has translational kinetic energy, what we think of kinetic energy previous to this, but it's also spinning by the end, right? If you watch something roll down a hill, it spins around its own center. So because of that, we actually split that MGH into both of these. So, and there's some substitutions in here that you can do, and that's, again, a lot of this you don't have to do. You don't have to do this part um, as much. And the process is the same for other shapes, but one of the things I want to hit on is this idea of what if we had something that didn't rotate, that didn't actually spin at all. Uh, it just slid down the hill. It would actually move faster because it would have all this energy, potentially, potential energy. And because it didn't rotate at all of that would go and have to be equal to just 1/2 mv squared. And if that's the case, that V is going to be bigger than if some of that potential energy had to get used up to rotate the object. So one of the problems I've seen before, it says something to the effect of, a ball and a block of ice, both with no friction, essentially, are going down a hill. One, the ball rolls down the hill and the block of ice slides down the hill. Which one is moving faster at the bottom? And they're both the same mass. And the answer is that the block of ice actually slides down the hill faster, even though they're the exact same mass. And the reason for that is it's only got kinetic energy linearly. It didn't have to use any of the energy that it had stored up potentially here to cause it to start spinning. So all of that energy gets put into moving it sort of through space, whereas for the ball, some of it has to be used to cause it to rotate. And typically that could be like a multiple choice question, and it would have two yes, or I'm sorry, two where it would say the block, and two that it would say uh, the the ball, with different explanations for why that is. Maybe one, or maybe it would have one of the answers that they roll down it, they get down to the bottom in the same amount of time. Um, the justification for that might be that the masses are the same. Well, that's wrong because the one spins. Maybe the ball because of some explanation that they give. But here, if you're going to have rotational kinetic energy, if you're going to have something that is going to roll, some energy has to be used just to make it roll, which means that it doesn't get as much for just translational kinetic energy. So if we had two objects that both rolled, the one that has the smaller moment of inertia will actually make it to the bottom more quickly. Less energy is going to have to be used to rotate that object to cause it to spin. So if we had, here a situation, if we had a race with a thin hoop, a solid disk, and a hollow sphere and a solid sphere, the order they would finish is here, and that's all dependent on what their moments of inertia are. The solid sphere actually has the lowest moment of inertia, then the solid disk, and then the hollow sphere, and then the thin hoop having the uh, most moment of inertia. So if you have less of a moment of inertia, that means that it is easier to spin. You have to use less energy to cause it to spin, and because of that, you end up getting a faster speed going down that incline. And that pretty much takes us to the end. Again, the biggest things here are not being able to do the calculations. Again, to be honest, most of the calculations are just not present. This idea of angular momentum being a conserved quantity is humongous. If there's no outside torque, the system conserves its angular momentum. If there is some movement within that system to get the mass closer to the center, it will actually cause it to speed up because that I became smaller, that omega has to become larger, that angular velocity has to be larger. But because of that, because both of those things change, they change proportionally so that that L, that angular momentum, doesn't change. The only way you change how fast or how much angular momentum something has is if you put an outside torque on it. And I should, be clear again, it doesn't even have to be an outside force. If you have a force that doesn't cause any torque, then the angular momentum is still conserved. It has to be a torque that causes that to happen. You have to add some angular momentum in with a torque, just like we have a net force to cause linear momentum to change. And I think I'm going to kind of leave it there. We'll go through some problems and some situations in the video tomorrow. I just want to sort of lay out some of those concepts. And again, I'll dive a little bit deeper with some problems and some situations in a video tomorrow. Hopefully you're keeping up, and I will see you guys in that video. I won't see you. You'll hear me in that video tomorrow.